Okay, so pause the slides while you have a little go at this entrance task, recapping equilibrium from last lecture. Okay, so what we should have said for A, which direction the position of equilibrium will be moved if more sulfur dioxide is added. Well, if you add more sulfur dioxide, the system will try and remove it and will move to the right, so you will make more SO3. B, how would increasing the gas pressure affect the position of equilibrium? Well, there are more moles of gas on the left. There's 1.5 on the left and just 1 on the right. So if you increase the gas pressure, it will move to the side with the least moles. Therefore, it will go to the right. This one here, how does the use of a catalyst affect the equilibrium? It doesn't affect the position of equilibrium. This is because it increases the rate of the forwards and the backwards reactions by equal amounts. Why is it used then? Well, that is because equilibrium, whilst it's not shifted, is achieved more quickly, so it's more cost effective. What we're going to look at today is quantifying equilibrium in the equilibrium constant, Kc. So what we want to be able to do is construct an expression for Kc for a homogeneous system in equilibrium. We want to determine the equilibrium concentrations of reactants and products using what we call ICE tables. Calculate a value for Kc from the equilibrium concentrations for a homogeneous system at constant temperature, and finally predict the qualitative effects of changes of temperature on the value of Kc. So the equilibrium constant, known as Kc, is a number that expresses the relationship between the amounts of reactants and products at equilibrium. If we consider this reaction, for example, how might we calculate a number that tells us about the amounts of reactants and products? What we could do is have an expression that looks like this, where we've got Kc, the equilibrium constant, is the concentrations of the product multiplied together divided by the concentrations of the reactants multiplied together. And this would give us an idea of which way the equilibrium lies. Now note in this, the square brackets are what denote concentration. So Kc is in terms of concentration, as shown in the square brackets, which mean concentration in moles per decimeter cubed. So if that's the Kc expression for the reaction at the top, pause for a second and see if you can write the Kc expression for this reaction. And what you should get if you do products over reactants is this. So that is the Kc expression for that reaction. Concentrations of the products over the concentration of the reactant. Moving on, if we look at this one, which is a little bit trickier, writing a Kc expression for this reaction, pause for a second and see if you can figure it out. So you should have come up with this. So this time, what we need to note is that we always put the big numbers at the front outside of the square brackets as a power. So there was just one case, which was k in square brackets, but it was 2m, so we have m squared. On the bottom, we've got h as just one of those, but it's h plus 2j. So on the bottom, you've got hj squared. Must all be in square brackets to denote that concentration. So this shows you the general equilibrium constant expression. So Kc equals each thing, so reactant or product concentration, raised to the power of the number in front of it. So in this case, the product C raised to its power, the number in front of it. If it's a 1, it's just not there. If it's D, it's to the power of little d. And then on the bottom there, concentration of A raised to the number in front of it, and the concentration of B raised to the number in front of it. So like I say, if the number in front is a 1, you don't need to put it there. So Kc is the equilibrium constant. Represents K in terms of concentration, hence the little c. The number in front of B in the equation is the power that B is raised to. The square brackets denote concentration in moles per decimeter cubed. So pause the slide for a second and see if you can write equilibrium expression. So pause for a second and see if you can write equilibrium expressions for those 3 examples there. So what you should have got is PCl3 Cl2 over PCl5, quite straightforward. This next one's going to need some powers. So the ammonia is raised to the 2 and the hydrogen on the bottom there is raised to the 3. And you'll also have powers in this last one because the HI needs to be raised to the 2. Okay, so we've now got some idea what Kc is, and we can construct expressions for Kc for homogeneous systems in equilibrium. We now need to look at equilibrium concentrations and values of Kc. So, if we look at this example here, the initial moles of PCl5 are 1.25. At equilibrium, the moles of PCl5 is 0.75. The volume is 1 decimeter cubed. Calculate Kc. So there's our Kc expression. So we need to know the concentrations of each of those species. So we know that at equilibrium, we've got 0.75 moles. We know the volume is 1, so we can just do 0.75 over 1, and that'll give us the concentration of PCl5. However, what information is missing, and how can we figure it out from what we have? Well, we are missing the equilibrium concentrations of the other species. How can we figure it out? Well, we can use mole ratios. So how do we do this? Well, we set up what we call ICE tables. So you can see one at the bottom there. So ICE stands for initial, change, and equilibrium. So the initial is the amount of moles at the start. So from the question, we know that there's 1.25 moles of PCl5. And if something's not mentioned, you can assume that there is none of it at the beginning. We know that PCl5 had 0.75 moles at equilibrium. We can therefore work out the change in PCl5. So you start with 1.25, you end up with 0.75. You should be able to see that that is a change of minus 0.5. So we know that the change there is minus 0.5. Now we can use the mole ratios in that equation to figure out the changes of the other two. So it's all 1 to 1. 1 PCl5 makes 1 PCl3 and 1 Cl2. So if I use up 0.5 of PCl5, I make 0.5 of each of PCl3 and Cl2. Since I know that I had none to start with, I now know that my equilibrium amount of PCl3 is 0.5, as is my equilibrium amount of Cl2. So I now have all of my equilibrium moles. I can now go about working out my Kc. So I'm going to need to use concentration as moles divided by volume for each. So for PCl5, it's 0.75 over 1, PCl3, 0.5 over 1, Cl2, 0.5 over 1. Now, I know that it's 1, so it seems a little bit pointless, but you must remember that you always divide by the volume to get the concentration. One of the most common mistakes in these calculations is to just plug in the number of moles and forget that the volume is there. So you must remember to convert to concentration before you plug the numbers in. So now if I look back at my Kc expression, I can see that I need to do PCl3 and Cl2 on the top and PCl5 on the bottom. So if I plug that calculation in, I will get a value of 0.33 as my Kc. Okay, here's another example. So pause the slide for a second and see if you can have a go at filling out this ICE table to get the equilibrium moles. So we know that we have 1 of methane and 1 of water at the start, and we were told that we had 0.4 of CO at the end. The starting concentrations or moles of CO and H2 weren't mentioned, so we assume that it is 0. So we can see, first of all, we can get our change in CO. So that has been plus 0.4. Now, if we look at the equation, CH4 and H2O and CO are all 1 to 1 to 1. So if I've made 0.4 of CO, I must have used 0.4 of methane and water. So their changes are both minus 0.4. Since they started with 1, I can now establish that their equilibrium moles are all 0.6. The hydrogen is a little bit more complicated. For every 1 mole of CO that we make 3 moles of H2. So if we made 0.4 moles of CO, we must have made 1.2 of hydrogen. We started with none, we've gained 1.2, so the equilibrium moles must be 1.2. So there is my completed ICE table. I can now do my Kc calculation. So the first thing I need to do is to convert into concentrations. So I need to divide each moles by the volume, and that will get me the concentration for each. We then look back at our Kc expression, and we need to plug the numbers in, and we should come up with 0.48 for our value of Kc. Let's just check we're happy then. So have a go at these two ICE tables for this equation here. So pause the slides whilst you try those. So there's your first set. So just check you managed to get those correct. And there is the second set. So just double check that you've managed to get all of those correct. So here's another example. So you need to pause the slides and have a good go at this question. Remembering, of course, you need to build your ICE table. Then you need to convert to concentrations and plug it into your Kc expression. So the first thing you need to do is build your ICE table and populate it with what you know. So you're given the initial moles of H2 and I2. HI is not mentioned, so we assume it starts at 0. And then you were told that the equilibrium mixture contained 3 moles of HI. So you can populate your equilibrium moles of HI. Next thing you can do is then work out your change in HI. So hopefully you can see that that is plus 3. And then from that you can populate your remaining 2 unknown concentrations. So if you've made 3 of HI, you must have used 1.5 of each of H2 and I2, which you can then get the equilibrium moles from, and both will be 0.4. From our equilibrium moles then, we can work out the concentrations because we are given the volume, not forgetting that 250 centimetres cubed needs to be in decimeters cubed. So you're going to divide that by 1,000. So we can do each concentration by doing the moles divided by 0.25. This is our Kc expression. So we can plug our numbers in and the value we should come up with is 56.25. The final thing that we haven't looked at then is what are the units. So for Kc, the units change, and for each one you have to work them out, and you need to know how to do that. So let's look at 2 examples of how we would do this. So if we look at the Kc expression at the top, we've got A, B on the top and C on the bottom. So that means we've got 2 lots of concentration on the top and 1 on the bottom. What we can then do is cancel out as many as possible. So we'll cancel out the 1 on the bottom and 1 of the ones on the top. And what we're left with is moles dm to the minus 3. So units of Kc in that particular case are moles dm to the minus 3. Look at the bottom example then. This time we have A squared on the top and B and then C. So that means we've got 3 lots of concentration on the top and 1 lot on the bottom. So if we cancel those 2, we're left with this, and then we need to multiply that out. So you multiply the powers, so we'll come up with mole to the 2 dm to the minus 6. This example is slightly more complicated because if we look in this case, we've got 1 lot of concentration on the top and 4 on the bottom. So there are now more on the bottom than there are on the top. So if we proceed as normal, we can cancel out 1 of the top ones and 1 of the bottom ones. And that leaves us with none on the top and 3 on the bottom. So if you've got none on the top, it's a 1. And then the ones on the bottom have multiplied out the left-hand side ones. So that's mole 2 dm minus 6. And left the right-hand one, it's just 1 now because I cancelled 1 of those out. But you can't leave this like this. So what we do is simplify down the bottom, just adding them together. And then we need to make them all on the 1 line. So if you move them up from the bottom to the top, you have to change the signs. So 1 over mole 3 dm minus 9 becomes mole minus 3 dm plus 9. So pause the slides again and see if you can work out the units in the 5 cases below. So pause and have a go. So the first one, you should have got mole dm minus 3. Second one, you also got mole dm minus 3 because there's still 2 on the top and 1 on the bottom. In this next one, you've now got 1 on the top and 2 on the bottom. So you're going to end up with 1 over mole dm plus 3. So you'll need to move it up and swap the signs. This one will be mole 2 dm minus 6. And this last one will be mole minus 2 dm6. Because again, you had more on the bottom than you did on the top. So we can now construct expressions for Kc for homogeneous systems in equilibrium. We can determine the equilibrium concentrations using ICE tables, and we can calculate values for Kc from the equilibrium concentrations for a homogeneous system, and we can also determine its units. So the final thing we need to do is predict the qualitative effects of changes of temperature on the value of Kc. So if we look back to our expression for Kc, it's shown here. You've got products on the top and reactants on the bottom. If your equilibrium is 1, that must mean that the top and the bottom are equal. And that means that there is exactly the same amount of products and reactants. The equilibrium is in the middle. If it's greater than 1, the top of your Kc must be bigger than the bottom. And that means that there is more C and D, so there is more products. If your Kc is less than 1, it must mean that the bottom, so A and B, is bigger than C and D. So in this case, you have mostly reactants. So if we think back to our previous lecture, we know that some conditions that can be tweaked for a system will change the position of equilibrium. So if we think back what changes we could possibly make, we had temperature, concentration, and adding a catalyst. So let's look back through each of these and see what, if any, changes they cause for case C. So looking at temperature first of all, this is an exothermic reaction. That's because delta H is negative. So that means from last lecture, you'll know we can label the exothermic direction. So the forwards reaction being exo means that the right-hand side is the hot side, as we call it, and the left-hand side is the cold side. Now, you wouldn't actually say that in an exam question. That is purely to help you decide which way the equilibrium shifts. So if we increase the temperature in this case, it's going to shift the equilibrium to the left to try and cool the reaction vessel back down again. This is going to mean that A and B will increase and C will decrease. So A and B on the bottom there are increasing, C is decreasing. That means that overall, because the bottom has increased and the top has decreased, Kc will decrease. So temperature can affect the value of Kc. You will need to be able to predict what it will actually do to the size of Kc using the system I've just shown you. Another thing that we could do is change the concentration. Now, if the concentration of any of the reactants is changed, the equilibrium shifts to minimise that change. And by doing that, it means Kc will not change. So concentration cannot affect the value of Kc. The whole point of equilibrium is that if you make a change in concentration, it will shift to restore the value of Kc. So concentration cannot affect the value of Kc. Finally, catalysts. If you think back, we did say quite clearly last lecture that catalysts do not move the position of equilibrium. They merely mean that equilibrium is attained more quickly. They don't actually change the position of it. That means that Kc will not change if you add a catalyst. So catalysts do not affect the value of Kc. I guess the summary really of the changing conditions then is only temperature can change Kc. Now, this is commonly forgotten. So in getting all tied up with working out changes in position of equilibrium and so on, people forget that only temperature actually changes Kc. So if you're asked what effect concentration has or a catalyst has, you don't need to think about it. It has no effect. Kc does not change. Only temperature can change Kc. So where you should now be at, you can construct your Kc expressions. You can use ICE tables to get equilibrium concentrations. You can calculate values for Kc and also work out the units. And you can also predict the qualitative effects of changes of temperature on the value of Kc. I've not included a concentration or catalyst there because we now know they do not affect the value of Kc.